Hi guys, in this video we want to demonstrate how to resolve a mixed constraint problem in linear programming. In our previous videos we've looked at how to resolve a maximization problem, a minimization problem, and here we want to show how we can resolve a problem that has both of them in, you know, there's a combination of the less than or equal to type and greater than or equal to type for inequality. So the steps are basically same, just to demonstrate how both of them can work together. So the first step will be to show the standard form, which basically is where we assume that both sides, the right hand side and the left hand side, are equal. So for this it's going to be maximize, so be the standard form, which is maximize profit, which is 20,500 A plus 4,500 B, subject to 5A plus 4B we will assume to be equal to 400. Then 6A plus 10B will be equal to 600, where A will be equal to 20 and B equal to 10. Of course, A, B will be greater than or equal to 0. That's the non-negativity constraint. So the next step will be to compute our coordinates that we use in graphing the constraints. So I'm going to clean this. Let me start from here. Let me do step 2 will be the computation of the coordinates. So for constraint equation 1, we have that 5A plus 4B is equal to 400. So we're going to hold B constant to derive the value of A. So 5A plus 4 by 0 will equal to 400. So that 5A will be equal to 400, where A will be equal to 400 by 5, which gives us 80. And we now hold 8 constants, which is 5 by 0 is equal to 5A by 0 plus 4B will give me 400. That is to say that 4B will be equal to 400, where B will be equal to 400 by 4, which is equal to 100. Now we'll clean this off and use it to compute our remaining coordinates. So let me record it here. Our coordinates we have A, we have for B, for 1, when A is 80, B is 100. 2. Now constraint equation 2 is when we have 6A plus 10B to be equal to 600. So we hold B constant, that is to say that we have 6A plus 10 by 0 will be equal to 600. Then 6a will be equal to 600, where a will be equal to 600 by 6, which gives me 100. Then we hold a constant, that is 6 by 0 plus 10b will be equal to 600. Then 10b will give me 600. b will equal to 600 by 10, which gives me 60. So in constraint 2, we have 160. Of course, for a in 3, we have 20, and for in b we have 10. So of course this is 0, this is 0. So with this, we can now go to the step 3, which is graphing the constraints, using the coordinates that we've computed. So we are going to choose our scales appropriately and now graph our constraints. Then after which you're going to test them, by testing the extreme corner points. So we will, step 3, graph the constraints. Graphing the constraints. So, of course, when you want to choose your scale, you look at the nature of your values. So you can see that they are intense. So we can choose ones here. So this is 0, this is my x, of course this is my a, this is my b, that's my x, this is my y. So because they're intense, we can choose 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. Of course, we have mentioned in our previous videos that when we use your graph to do this, you have more accuracy. So for this, we have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. So now with this, we can now graph our constraints comfortably. Now for the first constraint is when a is 80, b is 100. So and this is my a, 80, which is this point, and b, 100. So we're going to be linking 80 to 100, 100 in b, 80 in a, so pardon our inaccuracy in drawing. So of course, if you use your graph, it's just going to guide. If you use your graph, this is the line of um, um, the constraint equation. So we have 80 and 100. So, and our guide when we are shading of course, graphing the constraint is just an effort towards identifying the feasible region, which is the region that is that houses the combination of the optimal production, the optimal combination of production. So now, because it's of less than or equal to type, anything above the line is not desirable by us. So we're going to carve it out, we're going to shade it off. So we'll shade this off. Don't also forget, some authors will shade in the feasible region, but the effort is same. So if we shade in here that is desirable, it might definitely going to look so untidy. So our approach is to shade off the points, the parts that we do not want. So at point 2 we have 160 when A is 100. When A is 100, that is this point, B is 60. So we're going to find a way to link this. Don't mind us with our drawing. It has been mentioned severally that the more you use, when you use your graph, definitely you are going to achieve a better result. So this is just going to guide you. So this is our A, that is 160. So it is also of less than or equal to type. So anything above the line is not wanted, it's not desirable. So we're going to shade it off. We'll shade it off. Our approach is to shade off the parts that we do not want. Now, the next will be to look at the other constraints which appear to be the requirement, minimum production requirement. Now this is A equal to 20 or less. So for A is 20. So we're going to draw a perpendicular line to 20. So we're going to have something like this. Okay. So it is a line of the constraint of A equal to 20 greater than or equal to 20. So anything less than 20 we do not desire that. So we're going to shade off from 0 to 19.99999. So we're going to remove this. We're still on our journey to finding the feasible region. So now the last but not the least, which is the requirement for B, which is 10. So we equally draw a perpendicular line to B, which is 10, which is at this point. So at this point, is at this point. So because it's of greater than or equal to type, we do not desire anything from 0 to 9.99. So anything less than 10 we do not want. So we're going to shade off here. So having graphed all the constraints, we can now see that this place is our feasible region. and this is the region of a optimal combination of production. So the next thing is, if we are to test all this space, of course, our objective function is of the profit type, is of maximization case. So which means that this is a space of profitable combination. So any point we take here and measure, carry it out from here, read it out from here, you take this one from here and read it up to B. It's a combination, it's a profit combination. But it has been determined that the best combination will come from the extreme corner points. So we'll be testing the extreme corner points. We have them here. I have them to be, let me label this one N, which is 1. I have another one W. W is here, this one. Then I have K, let me label this one K. Then I have another one here, let me label this one Q. So I have N, W, K, and Q. So we'll quickly test them by reading them off, and imputing them in our objective function to find out their values. So this is A, this is B, point N, my A is 20, while my B, we can read them off here, that's this point. So let's just take 48. If you use your graph, it's going to be more accurate. Then at point W, we have A to be 20 and B to be 10. That is this point. A is 20, B is 10. Then at point K, let's take B to be A to be 68. Of course, B is 10. Then at point Q, we can measure this, read it off. This is about 60. This is 60. Okay, let's just take 60. A is 60. Then B is okay, let's take 23 or 24. Let's take 24. Alright, so the next will be to step number 4 will be to test the extreme corner points, which is simply to impute these values that we've read off into the objective function. And recall that our objective function is to maximize profit. Which is 2,500 A plus 4,500 B. So at point N, we'll have 2,500 by 20 plus 4,500 by 48. What do we have? Then at point W, It's going to be 2,500 by 20 plus 4,500 by 10. Then at point K, we have 25 by 68 plus 45 by 10. Then at point Q is 25 by 60 plus 45 by 24. Having determined the values for the combinations, we have seen that, of course, the objective function is a maximization case. So we're going to select the combination that gives the highest profit. So this is 266,095, 215, and 258. So this will be selected. So the optimal combination will be to produce A, 20, and B 48, and optimal profit will be be 266,000 naira. Alright, that's how to resolve a mixed constraint problem using the graphical method. Hope you find it relevant. I find this video relevant. See you in our next video. Thank you.